I think that's next price of the year. We still.
Should be good to go.
Good morning. Yeah, my homework 5. You want to go? We started discussing DC circuits. DC circuit means the voltage that is applied. DC here stands for uniform voltage, of it is called direct voltage. It should be contrasted with the situation where the voltage changes with time, and we will try to do that a little bit, not as much as one would like to do in this course, but about a week or so later on, we'll come back and do alternate circuits too. But here we are doing DC circuits, and we said there are 3 electrical components here. Just the thing, that's one is capacitor, second is resistor, and third is inductor. First and second we have already introduced, and the third one we will take some more time. We have to introduce the idea of magnetism to begin with. But to just give you a broad picture of what is up, this shows energy in electric field, and an inductor stores energy in magnetic field. Magnetic field will be termed as P. it is good to visualize this in the following manner. That's your capacitor. That's your two wires that is connected. So these are conducting wire and electric field. When you charge this capacitor, it is okay to think of it as the amount of charge decides how much energy there is in the capacitor, but it's helpful to think of this as stored in the electric field, which is in between the plates. That's a deeper concept when you think of the energy as stored in the space in between the capacitor, but the space is not empty in the sense that there is electric field, but there is no matter in there. There are no objects that have mass in there. So that's electric field. Similarly, we will later come and talk about an inductor. An inductor is like a capacitor, is simply two parallel plates. An inductor, we will see that that's just a coil. You twist a conducting wire in the form of a cylinder, and you make a spring-like object, and the magnetic field that is stored inside this coil, not outside, inside. Similarly, the electric field is stored inside the capacitor in the space inside the capacitor, and this will be magnetic field. You'll see that later on in more detailed expressions for that, but now the only thing we need to know is that it stores energy in the form of electric field. Inductor stores energy in the form of magnetic field, and resistor dissipates energy. Or lose energy there, and mostly in the form of heat. By heat, we mean there are charges that are moving around, and the energy that is stored in the electric field and magnetic field is used up by the electrons, and the velocity of the electrons, let's say, this decreases or increases, and it increases its temperature. And in that sense, it is lost in the form of heat. We have introduced very simple circuits, mostly series and parallel, but not every circuit that we can think of will be in series and parallel. So in those situations, we want to have a slightly more general rules with us, instead of just having the idea of parallel and series. And these are called Kirchhoff's law, and the advantage of this is that they can be used in a localized circuit instead of having the complete circuit under analysis. So we can just think of one loop in a circuit, even though it's an extremely complicated circuit. We can just think of a localized region where there is a loop form, and we can still conclude a lot of things. So that's what we want to talk about today. Kirchhoff's rules. There are two rules. First one is called the junction rule. But this is just a name given. This is nothing but what we have already seen. It's a consequence of conservation of charge. We have right from the beginning assumed that charges cannot be created or destroyed just out of nowhere. You can only move it from one place to the other, one material to the other. So you cannot create a charge or destroy a charge. If you can create a positive and a negative charge. That's zero, remember, right? So you can have an electron and a positron that's created. That's perfectly fine. Or even a proton and an electron, as far as the other form of energy is there in some other form, but charges have to be zero or conserved in any process that we are considering. So how do we use this? Take any junction, that's what junction means. So think of a junction where there are 3 or 4 electric wires coming in and joining in, and typically we are talking about current. So I1 coming in, that could be I2 going out, and I3 going out. Let's say I4 going out. It doesn't matter these directions. We use the rules accordingly. Let's say from this point, you talk about whatever is coming in is positive and whatever is going out is negative. And in that case, you would say this is plus I1 minus I2 minus I3 minus I4 is equal to 0. That's junction rule. Take any junction in a circuit, it could be a complicated circuit. I'm not saying I have not given you the information about what kind of component is connected here. This could be a resistor, capacitor, and that could be hundreds of things connected there. But take a localized region in a circuit, a junction, where one or more wires come and leave. And the rule is that the current has to be conserved there, or whatever current comes in has to go out. It is a consequence of conservation of charge in the sense that current is nothing but derivative of charge. So it's the time derivative of Q1 minus Q2 minus Q3 minus Q4. Which means that the total charge is constant. In that sense, it's conserved. Conserved means it doesn't change. That's a constant, and that means that the total charge is conserved. So that statement, when you're working in electrical circuits, conservation of charge is better used as the current is. You don't think current is conserved in the sense it's not constant. Whatever is coming in goes out. So that's the simple rule. This can be imagined to be like a water flow. That is water coming through a pipe. You don't the water doesn't cannot disappear in a plumbing line. Right? So whatever has to come in has to go out. And even if there is a leak, you have a pump of that leak, and then you get that going out, and there is a negative flow of water. So that's a simple rule, and we'll try to use this very soon and see how this works. The second is called the loop rule. And this is a consequence of conservation of energy. We have talked about electrostatic force being conservative. By that, we mean that the work done by the electrostatic force when a charge moves around in a circle is 0. And that's what we mean by the conservative force. That means that the potential energy or the change in potential energy for the electron when it goes in a circle is equal to 0. Or instead of potential energy, we can talk about electric potential. The change in electric potential between 2 points in anywhere in space. You take 2 points, you go somewhere there, and then you come back. It doesn't depend on the path. And as far as you come back, the change in electric potential has to be 0. Electric potential, now we are not talking about gravitational potential. Separately, we are independently saying that gravitational potential also is conserved. That means to say that in any loop, for example, let's consider a simple loop here. So that is a battery, and a resistor, and a capacitor. So that's the 3 components that we have talked about, and they are all in series. Let's say we will later, half an hour or so later, we'll do the circuit in more detail. But we just have to start from anywhere in this circuit. Let's say we start from here. We go along a loop. So you say this is V. Let's say this is VR, and that's VC. What does VR and VC mean? This is the drop in potential when you go across the resistor. This is the drop in potential when you go across the capacitor. You'll see this in more concrete form when we are doing different circuits. But if you go in a loop, so let's say A, B, C, D, and then come back to A. So A, B, C, D, and then come back to A. What loop rule says is that the change in the electric potential in a loop, it doesn't matter whether it is this loop, but as far as you come back to the same point, that has to be zero. In this case, that would mean that plus V, here it is dropping, so it will be a higher potential here and lower potential here. So you would say this is minus VR and minus of VC because this is the source of energy. This dissipates energy. This doesn't dissipate, it stores energy, but then it takes away the energy in there. So in that sense, it dissipates. So that's equal to zero. So those will be the two rules. We should be able to write down equations associated with that, and that will help us find unknowns in or analyze the circuit or find unknowns if next. So that's the concept. Last time we talked about resistors in parallel, and we did that in a hurry because it was in the last few minutes. But let's do the same problem here, or the same configuration here. But this time, let's use Kirchhoff's rule instead of the idea that current goes from one resistor to the other resistor and talking about that. So let's say resistors in parallel. We have two resistors, or one, or two, parallel circuit, and that's voltage V. Let's say this is R1 and that's R2. That's a system. We go to the market and purchase R1 and R2, or you design these resistors R1 and R2, these are devices. And V is the voltage that you connect to this resistor. And what the system does is decide how much current it will allow it to go through these resistors. So the question is how much is I1, so that's the unknown, and how much is I2. Let's say R1 is equal to 100 ohms and R2 is 200 ohms. And voltage could be 10. And the question is, what is I1 and I2? Two unknowns and rest of the quantities are given to us. And you would have used the equations that govern parallel circuit or resistors in parallel. But now let's use the junction rule and the loop rule. So let's say that the current that is coming out of the voltage is current I. So this forms a junction here. So there is current I that is coming in. I1 goes this way, I2 goes in the other direction. So junction rule at, let's say, let's give some names. So there's A, B, C, D, E, F at junction B. So at junction B, we immediately say that I minus I1 minus I2. So whatever I is coming in has to go out. So there is I equal to I1 plus I2. Right, that's a simple equation we have. Earlier, we would have said that it has, so current is like a flow, and whatever is coming in has to go out. Same idea here. We are saying it's a junction rule or it is a conservation of charge. Next, To get more equations, let's say loop rule. Loop, how many loops can you form in this circuit? In general, there are three loops that you can form. One is A, to B, to E, to F, and then to A. That's one loop you can form. And you can also say A to B, to C, to D, to E, to F, and then to A. That's the second loop you can form. But of course, you can also have this as a loop. It's not necessary that you always have the voltage in the loop. There is a third loop possible. So that's B, C, D, E, and B again. So let's call this loop 1, let's call this loop 2, and let's call this loop 3. And each of these loops gives you an equation. Not necessarily all of them are necessary to do this problem. All of them may not be independent. So let's talk about loop 1. Loop 1 is AB. So this is a small loop that I'm pointing out to here. So you start from point A to B. This is a conductor. 2 points on a conductor, there is no potential difference, so that you don't lose or gain energy here. A to B, you don't lose any energy, you don't gain any energy. B to E, it's a resistor. Remember, a resistor consumes energy, and at this point, it is also necessary that are you going in the direction of the current or opposite to the direction of the current? If you're going in the direction of the current in a resistor, you lose energy, so it's minus. On the other hand, if you were to have this I2 as in the opposite direction, in a more complicated circuit, you may not be able to intuitively tell what is the direction of the current. Choose any current you want to. Choose the direction, whatever you want to. Even if you have chosen the direction in this way, your answer will come out to be negative in the end. When it comes out in the end as negative, you flip it or you interpret it as actually the current was going to the right. Here we have chosen it the right way. So notice what we are saying is minus I2 R2. Remember, voltage across a resistor is current times resistance. So it is minus because resistor consumes energy, or it is consuming energy from the battery, or better, that is a potential. This is at a higher potential, that's at a lower potential. That's the basic idea. Whenever you go from a higher to a lower, in the final minus initial, so it is minus sign. E to F, there is no potential difference. It's a conducting wire. Conducting wires do not have any potential difference. F to A, you're finding a potential. You're going across the battery. You're going from the lower potential to a higher potential. So it's a positive read. That's plus V equal to 0. It's equal to 0 because you completed the loop and you make it 0. Notice your loop rule immediately gives you the equation which we would have used the potential difference of across 2 points get the for resistors, or we got that using different arguments earlier. Let's do loop 2 now, and you come back and put the numbers here. Loop 2 is A, B, C. So you go from here to here, there is no potential difference. So then there is minus I1 R1 and plus V is equal to 0. So you go from here to there, no potential difference. Here to there, you drop, and there is a drop in the potential. The final minus initial is minus, and here you increase, or you go from a lower potential to a higher potential. So it is plus V. Let me write down loop 3 also. Usually, even though we are writing down 4 equations, there are only 2 unknowns. I1 and I2, there are only 2 unknowns. So you need only 2 of these equations, and other equations will be identical. You won't get any more information than that. But what I'm pointing out to is that all of us might pick different loops to work with, and that's okay. You can pick your own loop and it will lead to the same answer or same analysis. Loop 3, you go from B to C. So you're going from here to there. Here to there is higher to lower potential. So it is minus I1 over. So you have reached D now. D to E, no difference. Then you go from E to B. When you're going from point E to B, you're going against the current. That's one way to look at it. Or you also know that this is a lower potential, that's a higher potential. So you're going in the opposite direction of the slope. So you gain potential. So it is plus I2R2. Make sure you recognize to differentiate between why this is plus, why this is minus. A simple way to do this is, if you're not very familiar with how to analyze potentials yet, is to look at the direction of the current. If you're going against the direction of the current that you chose, this could have been a wrong direction of the current, but whatever is the direction shown in the diagram, if you're going against the direction of the current, you use plus sign, and if you're going in the direction of the current, you use a minus sign. So that's a rule you can use to get the same equation. Otherwise, try to analyze whether this point is at a higher potential relative to this. So that's the idea. So what we have these 4 equations. Let's see what we can do. Let's put in the numbers. So we have this is all 3 are unknown, so we cannot write anything more than this. But in here we have numbers associated with this. So this is 10.0. We write it down as it is. So minus I2 times 2 is 200 plus 10.0 is equal to 0. And this one is minus I1 and 100 plus 10.0 equal to 0. And here we have minus I1 times 100 plus I2 times 200 is equal to 0. All this should be consistent. Again, as I said, there are only 2 unknowns. We need only 2 of the equations, but nevertheless, all the 4 equations should be consistent. So let's see how it is. At least in this case, this immediately implies you can solve for I2 here. So I2 is 10 over 200. So that's how much? 10 over 2 is 5. So then 5 divided by 100. So that's 0.05. And you need 360 digits. So it's 0, 0. So that's amp. And I can also say that's 50 milliamps. I1 using this equation, and here it is equal to 10 over 100, which is 0.10. So that's 0.100 amps, or you can say that's 100 milliamps. So that's your 2 answers, but then since you have written down other loops, you can check your answer. That means to say that this should be consistent. If you're doing this as an analysis, you got to make sure that you haven't made any errors. So this is a consistency check. So if you plug in these numbers, it is clear that I1 over I2 is 2, right? So this implies that I1 over I2. I1 divided by 2 is 200 over 100, which is 2.00. And that's exactly the case, right? 100 divided by 50 is 2.00. So that's set, consistent to check, and that is okay. We can now go in here. So this tells us how much total current does this 2 resistors pull from the voltage V. So we know that I is equal to I1 plus I2, which is equal to 100 plus 50 plus 150. 3 digits milliamp. We can also talk about equivalent resistors that deals with a circuit where these two are replaced by a single resistor. So then you would say this is V over R equivalent equal to I1. We said here is V over R1, right? So this is V over R1 plus V over R2. And this gives you R2. This we can calculate R2. That's not very informative because that doesn't use this feature of junction and loop rule so much. So that's a simple exercise that we can do, but these are all resistors in series and parallel. So let's do a more slightly more relevant circuit. Before that, let me do a very simple exercise. All right. Let's think of a let's say this is R1, that's R2, and that is a V2 here, and let's say that is a V1. So, and let's say V1 is equal to V2, and let's say both of them are 10 volts. So that's 10 volts. And R1, let's say 100 ohms, and R2 is 200 ohms. And the question could be what is the direct, how much current flows through I1 and how much current flows through R2, because it's a single loop, whatever current goes in here has to come in here. So the simple conclusion you immediately make is I1 is I equal to I2. Pick any junction here, so here or here. It's a single circuit, so it has to go through. It may not be obvious what the direction of the current here. Does it go to the right or to the left? In what direction does the current go through? Will the current go to the right or to the left in that circuit? Right. Okay. Any other suggestions or answers? Both and moles. Yes. So the hint is they are both 10 volts. So there will not be any current. So the answer is then no current because both are at 10 volts. So this potential is exactly the same as that potential. The potential at those 2 points is the same. If there is no potential difference, there is no movement, right? It's like saying if the flow was perfectly horizontal, you put some water here, there is going to be no flow. Like if the potential is going to be exactly the same electric potential, there will be no current that will go through. Same thing in here, these two are exactly at the same potential. So I1 will be actually 0. I2 will be equal to 0. Only if V1 is equal to V2. So that's a simple analysis we can make. But let's now actually do a circuit where it is necessary to use Kirchhoff's loop rule and junction. So let's have the following circuit. V1, let's V2, and let's have a third resistor here for R1, R2, R3. Let's say this is 10 volt. This is 20 volt. So that's 200 ohms. Say 100 ohms, and let's say that's 300 ohms. Which of the resistances in this are in parallel? None of them are in parallel or in series. So this circuit cannot be analyzed using the ideas we have learned in series circuit and parallel circuit, because this is not in series because there is a third resistor going in. These two are not in parallel because there is a voltage attached here. These two are not in parallel. So none of them are in parallel, none of them are in series. So it is not very useful if we just analyze it using using series and parallel also. But instead now we will use loop rule and junction rule. So let's randomly, we don't know, it is not very easy a priori to argue which direction does the current go through. This is at a higher potential, we expect the voltage to go through, but this is also at a higher potential. So maybe the potential here to here, it could be this way or that way. It is not a priori obvious as to this is at a lower potential related to this or at a higher potential, because it is lower than 20. If this was at 16 volt, for example, in that case, current will be going in this direction. If this was 9 volts, then this current will be going in the other direction. So we don't know a priori what is going to happen. So guess, like let's say that this is I1. In the end, if the answer comes out to be negative, that means your guess was wrong and you have to fix it. So notice this is a guess. So that's a guess. The direction of the current is a guess, and most probably this is a wrong guess. So later on we will get a negative answer. I purposely am doing that so that at the end you get a negative answer and we interpret it as a negative number. Let's say this is I2, and that's whatever comes in here, that's I3. We immediately have one relation, junction rule. So I say this is A, B, C, D, E, and F. Junction rule at C gives us I2 has to be equal to I1 plus I3. Right, I2 is coming in, I1 and I3 is going out, so I say I2 has to be equal to I1 plus I3. And there are how many unknowns? That is I1, I2, and I3 are unknowns. Okay, that's the always the currents is what we are looking for, current or torque. That's what we want to find out. We immediately have this relation that means to say that out of the three two can be, if we know two, then we can solve for this. So let's build two loops. So it's convenient to build this as one loop, that as a second loop, or you can build the outer one also as a loop. So let's do the side by side loop. So let's say loop A to B to C to F to A again. So we will have, when I go from A to B, I'm going from lower potential to a higher potential. So that's plus V1. From B to C, notice I'm going to go use the direction of arrow as my signal. Current goes from higher potential to a lower potential. That means this is at a higher potential. So when I'm going across the resistor, typically it should be minus if I'm in the direction of the current. But here I'm going against the direction of the current. So I'm finding a potential. So that means it's plus. Notice that's, make sure you understand why that's plus and not minus. I1, R1. And here we are going in the direction of the current. Current always goes from higher potential to a lower potential. So this is lower potential, that's higher potential, according to the convention of the current. So it's minus I3, R3. Minus I3, R3. And we come back to the same point, that's equal to 0. So we have found an equation like that. Let's do the other loop. Let's say start from E, go to D, go to C, F, and then come back to E. That's another loop possible. This time you're going from across V2, you're climbing a potential, so that's plus V2. Again, remember, that could be situations when you're going this way, then you're going from higher potential to lower potential, then you would say it's a minus V2. But now we are going E to D, that's plus V2. We are going in the direction of the current. Current always goes from higher to lower potential, that's minus I2R2. Minus I2R2 again in the direction of current. Current goes from higher to lower potential, so it is minus I3R2. Is equal to 0. That's the three equations. We have three unknowns. We have three equations that are sufficient to work with it. You can go ahead and make another loop there, and that could be used for consistency check. But let's work with these three equations. Let's immediately rewrite this. Let's first replace I3 in terms of I1 and I2, so that I have only two unknowns left. I3 is I2 minus I1. So that's plus V1 plus I1 R1 minus of I2 minus I1 times R3 is equal to 0. Put in the numbers if you want, or maybe you could put that. Let me put the numbers here itself so that it's not too many variables confuses you, right? So it's plus 10 minus R1 is 100, 3 6 digits, 300 I1, and minus I3 is I2 minus I1. 3 is 300. Rewrite this equation as a minus 100 plus I1, right? So that's plus 300. So that's 200 I1 And then there is minus 300 IQ. And I take the 10 on the other side, that's minus 10. That's your first equation. Do the same thing for this. So that's plus 10 minus IQ times 200 minus I2 minus I1 times 300 is equal to 0. Question? Yes, I made a mistake.
The 100 I one is supposed to be positive.
This one?
No, red was, yeah.
Ah, that should be positive. Ah, thank you. So this should be positive because that's good. Okay, thank you. Yeah, okay, so that's again, let's do this plus, thank you. Plus 100 plus I1, so that's plus 400 then, correct? Suppose. 7, thank you. Otherwise, at the end, I would have to spend time to figure this out. Yes.
That 10 meters, I think we minus.
Yep,
Yeah, for your second, you have plus 10, you will be plus 20.
oh, here, oh, yes, 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 yes. Lots of this. Thank you very much. I would have struggled at the end to find out all this error. Yeah, it's good to have many eyes. Finding out, okay, thank you very much, okay. Okay, so let's try it again, so. This is. Okay, did I do this? Yeah. Okay, I1, yeah, I1 is plus 300, that's plus 300 I1. Minus 200 and minus 300 plus minus 500 I2. Correctly, if I'm making things. So let me write that down here. That's 300 I1 minus 500 I2. And that's equal to minus 24. That's two equations, two unknowns. You can solve for this. So I1 would be equal to any simple ways you can think of. I'm just going to. So I'll write these numbers down like this: 400, 300, there. Do it your way, whatever find convenient. You can write these four numbers here like this, and I'll write. When I'm solving for I1, the equation is 400 and 300 is minus 10. Minus 20. And this is minus 300 and 500. That's a straight way of doing this. And then what you do is multiply the diagonal and then subtract the other multiplication of the other diagonal. So this will be minus 10 times minus 500 minus of minus 20 times minus 300. And the denominator will have 400 minus 500 minus of 300 times minus 300. Okay. How much is this? Help me. So in the denominator, you get a negative number for sure, right? That's negative, so that 3 into 3 is 9, 5 into 4, 20, 20 plus 5 into 4 is 20, 3 into 3 is 9, and 20 plus 9 is 29 with 4 zeros. But the zeros will cancel out from the numerator. Okay, in the numerator, there's a 3 zeros, that also has 3 zeros. This is a positive number. This is a negative number. So we get a negative, so we got a bigger one, right? 3 into 6. And that's 5, right? So that's 6 minus 5, that's minus 1. And 3 zeros. And it has to have 3 big digits. Am I
I think the bottom's wrong.
wrong?
Is that 400 times negative 500?
Yes, 400 times negative 500.
And then negative 300 times negative 300? Right there. or whatever.
300 times, yeah, negative with the front, yeah.
So I put it next to the figure, 110,000.
100, okay, so I did it wrong, okay, again. 4 zeros, 5 into 4, 20, 20 plus 3 into 3, 9.
I think you added them and didn't subtract them.
Oh, because this is opposite sign here. Yeah, sorry. Oh, yes, so it's 11 then? Yeah. Well, it's not a good day. Too many mistakes. Better?
Yeah.
Thank you. Okay, sorry. Did I get this right?
Yeah.
Okay, thank you. Okay, so 3 zeros, yeah, that comes a lot. Okay, minus, and did I get this minus sign corrected? No, right?
No.
Minus and the plus, yeah, I did fine. Yeah, okay, good. So it's plus 1 over 110. And how much is that? That I cannot do. So that's 9.1 millions plus 9.1. The plus sign means that this is I won, so this is correct. So I said it's going to be a wrong answer, so that says correct. Yes. Well, I intended to do it wrong, yes, but it didn't work. So that what that means is that this is at a higher potential. This point is at a higher potential than this, and the current is actually going to go in the opposite direction to that battery. So that's it. Again, that tells you that that's a non-trivial feature. You cannot immediately gauge through that. And do check this number, but it seems like yeah, at least one. Yeah. I said milliamps.
Yeah,
That's one of them.
It was 9.09. I rounded off. 9.1 milli. Yeah, only 3 zeros. So it's 1 over 110. Okay. Correct me. Okay, then the next one, right? So next one I just have to do the numerator. So IQ would be equal to, in the denominator I have minus 110,000, and the numerator would be 400, 300, and this is minus 10, minus 20. Okay, so that's equal to 400. Let me write that again. 400 times minus 20.0 minus of 300 times minus 10. Okay. That's minus 110,000, and that is for that's a negative number. That's a positive number. 3030 4 into 8 minus 3. 5. So it is 5,000 divided by 110. It's minus and a minus. 1,000, 3 zeros goes away. So it's 1 over 22. So that's 45 milliamps. Am I correct? My,
Oh, yeah.
okay. So that's yes, please.
If you want to put in your answer refraction, what would it be?
Oh, it will be still if if you leave it here, this will be just amps. So the answer is expected to be amps, but then instead of writing decimals, I just rounded it off in this way or that way. So yeah, here, whatever answer comes out here, that will be in amps. The SI unit for current is amps, right? Like in distance, we always write meter. If we are not using any units, then we want to convert it to meter. So here is amp. Coulomb per second. Okay. Any question here? So some form of this question is always there in the exam, at least in the last few years, if you take it, it's always there. One form, it won't be exactly this. I may not have I3, sometimes I have I2 in different forms. I can change these things in some form or the other. And so basically an application of Kirchhoff's law in a non-trivial circuit. Okay. So we are combined resistors, non-trivially in the sense they are either in discrete nor in parallel. But now that we have resistors and capacitors, a good thing to do is to connect them together. We can connect them in parallel or in series. Here, another example of connecting them in series. This is called RC circuit. So first, we had a set of 3 independent components. First, we collected 2 resistors, connected them to capacitors, connected them in series or parallel. And now we can take 1 resistor and 1 capacitor, and that becomes a good elementary circuit, if you want, and that's called RC circuit. So how does this look like when I connect them in series? A resistor and I have a capacitor. That's your R, that's your C, and that's your voltage. What happens when you connect a capacitor is this is a storage of charges. These charges move from this battery onto the capacitor. And they do that slowly in the sense that there's a lot of charges. The first charge goes pretty much freely because there is no resistance to that, in the sense that there is nothing repelling. But once the first charge comes and sits there, the second charge easily moves on, but then it gets a small repulsion from this. The second one will have more repulsion because there is more charges in that. And as time passes, there is a significant resistance or repulsion from the existing charge. And eventually, the expectation is that it will have a lot of charges there, and there will be a saturation. Right? There will be a time after which there is no current that flows in. And that leads us to ask, how much time does it take to charge a capacitor? So what is the time taken to charge a capacitor? So that's going to be our analysis. And for this purpose, we write down our Kirchhoff law, right? So we have, from here, we go plus V. We find the potential through the battery. There's a higher electrical potential here. And then there is a current that is going to flow through the resistor. It's going to go from higher potential to lower potential. So it is minus I and R. And here, you're consuming the energy, the capacitor is consuming some energy, it is storing the energy in the form of electric field. So you're still losing energy as far when you're talking about from here to there, you're losing energy into electric field. And how much is the potential difference across a capacitor? It was given by charge by capacitance. So this Q over C. So 1 week back, we did that. And that whole thing has to be equal to 0. Battery, resistor, capacitor in a loop, they have to equal 0. How much charge goes through this resistor is determined by rate at which charges are going. That's derivative of charge with time. So I can replace this I with dq by dt. So I learn, so let's say, you allow me to write this, so it's R Q by dt minus Q over C. And Q is the charge that is collecting on this capacitor. That's a time dependent quantity. This is not a linear equation anymore. This is first of all a differential equation, so we need to be able to solve this. So let's take dq by dt on one side and bring everything else on the other side. And I also will divide out by R. dq by dt equal to, I'm dividing out by R, so that's minus Q over RC, and so I will also do V over R, and I need this Q over C. That's Q. We go slow, Q over C plus, oh, that's the R, yeah, that's what I was doing. R also because I divide outside by that. So R over C plus V over R. I just rewrote this equation as dq by dt divided out by R, then it's Q over RC, R goes here plus Q over R. Let me write this as dq by dt is equal to, bring out the what should I bring out? What should I bring up? That's current, so I should bring out V over R. V over R. I bring out, so that's equal to Q. And I brought out the R, so PV is something is wrong. I didn't start. Why am I struggling? Yeah, do this like this. Sorry. So this is 1 over RC. Can be written in this form also. So Q minus R has been pulled out. C is there, so this is VC. That should be okay, correct? V times C is short, yeah, hopefully. Surely this is not wrong, it's just that can be, if I do the right thing, there will be less number of steps. Okay, so that's a differential equation. I have a solver. And you have probably studied differentiation and integration, but this is now involving both in a sense. Okay. I have a solve for Q here, but it is not algebra, remember? I cannot take out this Q, it is a change in Q that depends on Q itself. This is like typically population also depends on the rate at which population is increasing depends on how much is the current population. So in that sense, how much charge there is, or how much, what the rate of charge depends on how much charge there is in this capacitor. The current depends on the charge on the capacitor. To do these problems, rewrite this equation as get all the charges on one side. So Q take it on the other side, so it's Q minus BC. And take the time on the other side, BC over RC. So that's a very simple, or that's first, one of the first differential equation you will come across, that you have a first derivative is equal to the function itself. You can ask derivative of what gives you back the function itself with the negative sign and so on. And you will remember that it's an exponential function, and this will turn out to be a exponential function, except that you have to put this in the right place, and that's what I was trying to do. If you keep it in the right place, then it comes out neat. That's your equation. You have separated your charge, the two variables, the charge and time, and you immediately notice that if this is time and this is charge, and here also that is a charge, dimensionally speaking, RC should have the time. So a resistance and a capacitance is a time. And this actually is going to be our scale that will decide how much time it will take for the capacitor to charge. We are looking for how long does it take for the capacitor to charge. Immediately it is R times C in a sense of a scale. But there will be some interesting features in here. This is only a scale. This is not really the time that it takes. Similarly, there is a BC here. That's what I'm saying. Same dimension as charge. So B times C is charge. That's a scale for the charge. How much charge will be accumulated on the capacitor when it is completely charged will probably depend on it. Nevertheless, these are two variables separated out. Integrate on both sides. It is happening in a certain amount of time. So integrating slowly, it is going to collect the charge. This is an integral of the form dx over x. Dx over x minus, let's say, a. What's that integral equal to? What? Good, natural log. So this is log of x minus a. Very good. So this is equal to natural log of q minus bc. And that's equal to, that's a constant. R and C does not depend on time. That's the property of the capacitor and the resistor. So that comes out of the integral, and that's an elementary integral, that's T over RC. I'm interested in solving for Q. Whenever something is inside the natural log and you want to solve it, you invert the natural log, and invert is done by taking an exponential. You take the exponential on the left, exponential on the right, exponential and the natural log cancels out, and I have the charge minus a constant is equal to exponential minus T over RC. And something missed. Yeah, what did I miss? It is not a good thing. When I integrate, there is always a constant that I miss. If you're doing an indefinite integral, you have a constant there. That's a constant. When I take the exponential, this becomes an exponential of the constant. That's a new constant. And let me call that constant Q naught. of, I mean, just say. Sure. But that's an integral constant, that's arbitrary, we should determine it, so to do that, we need to give some initial condition. So let's now look for an initial condition. So this problem cannot be proceeded unless you give some information about what happens at some time. So you say that at time t equal to 0, at time t equal to 0, what was the situation? At t equal to 0, we said there is no charge on the capacitor. All the charges or all the energy was in the battery, so there was no charge on the capacitor. So Q was equal to 0. So that's a condition, and I can use that to solve for Q naught or determine Q naught. So that tells me that 0 minus Vc is equal to Q naught and exponential of 0, because that's the time. That immediately tells me that Q naught is equal to minus Vc. Put that in here, I get a solution for charge. Charge as a function of time is equal to Vc times 1 minus exponential of minus Q over RC. That's the growth of charge on the capacitor. And how does this look like? It is good to plot this instead of interpreting this. We have time here, and we're talking about how much charge is accumulated on the capacitor as time goes on. At time t equal to 0, this is 1, t equal to 0, exponential of 0 is 1, 1 minus 1, that's 0, so I start from 0. As time goes on, let's take an extreme limit where t is equal to infinity. At t equal to infinity, exponential graph grows. Exponential of minus infinity looks like this. Exponential of minus x, so it goes to 0 here, and that's the maximum value. So that's the maximum charge that it will apply. We see, and this is an exponential function that looks like this. So one can ask, what is the maximum charge that will be collected on the capacitor? It will be voltage times the capacitor. But more interestingly, how much time does it take for that charge to collect? It will actually never reach that. It is infinity. Yes, that's true, but to 2 significant digits, you can say that once you get about 98%, that's about when it collects the full, and you decide on a scale, an exponential function really doesn't have a scale here. So you have a set that when it happens, so a definition typically is that if you get 63% of this maximum, that's defined as a time constant. So this is a time constant. So tau, that's your time constant. The point is that since it takes infinite time to saturate the capacitor, you instead say at what time does the capacitor collect 63% of the total charge, and that's called the time constant, and that's given by RC. So if you have a resistor, typically of about 10 raised to 3, just to get an order of magnitude, 10 raised to 3 ohms, capacitor we said could be about microfarad, so that's 10 raised to minus 6 farad. Then the time constant would be R times C, that's approximately 10 raised to minus 3 seconds. That's about a millisecond. So a capacitor takes about a millisecond to charge. That's almost immediate, but nevertheless, it does take that much of time, and that plays an important role in the electrical circuit. In this case, I'm talking about charging a capacitor. You can immediately remove the battery and have a already charged capacitor, and you can discharge a capacitor. And the equations go very similarly, but the analysis is slightly different. You'll see that in your homework, and I will stop here. Thank you.